stand in the very middle of the floor and look straight up. Not at the walls, not at the gold, up into the ceiling, because the ceiling is the whole reason you're here, and the ceiling is doing something your eyes do not want to believe. You're under an enormous dome, a single, vast, curved sky of stone and brick, wider across than a city street, spread out 180 feet over your head. And it is huge. It feels like the inside of the sky got captured and hung up in a building. But that's not the part that stops your breath. The part that stops your breath is that the dome doesn't seem to be sitting on anything. Around its whole rim, right where it should be pressing down hard onto solid wall, there's instead a ring of windows, a necklace of light punched straight through the base of the dome, so that a bright band runs all the way around it, and the great heavy shell of the ceiling appears to hover above that light with nothing holding it at all. It doesn't read as stone. It reads as if someone unhooked the roof from the earth and let it float. 1400 years ago, a man stood roughly where you're standing and tried to describe this exact feeling. And what he wrote was that the dome seemed not to rest on solid masonry at all, but to be suspended from heaven by a golden chain. And standing here, head tipped back, you understand him completely because that is precisely what your eyes are reporting. A hundreds of tons lid of masonry floating on a ring of light. So you ask the only question that matters. What is actually holding that up? Because a dome is heavy, and a dome is greedy, and a dome does not want to float. A dome wants to fall, and worse than fall, it wants to burst. And this one has been hanging over this floor, through fires and sieges and earthquake after earthquake after earthquake, for very nearly 1,500 years. So let's work it out. Not with wonder, not with faith, with forces. Where's the weight? Where does it want to go, and what exactly is stopping it from getting there? Because the answer is one of the boldest, riskiest, most brilliant things anybody has ever done with brick and mortar, and I mean risky. Because the honest version of this story is that the first time they built this ceiling, it came down. Let me show you. My name's Dan. I build things for a living. I'm a structural engineer. 20-odd years of hard hats and high-vis and safety inspectors and budgets that never survive contact with reality. On a normal week, you'd find me arguing with a contractor about a steel connection, with a spreadsheet open that tells me, to 3 decimal places, exactly how much load every bolt can take. That's the job. Numbers, margins, certainty before you build. And I came here to this dome because it breaks my brain a little, and I want to be honest with you about why. There's one specific problem at the heart of this building, one geometry problem so hard that for centuries nobody had really solved it at this scale, and once you see it, you can't unsee it, and the whole rest of the story hangs off it. So let me hand it to you the way it was handed to the men who built this. Here's the problem. A dome is round. A room is square. That sounds like a riddle. It's a nightmare. Think about it. A dome, a proper hemisphere, a bowl turned upside down, sits naturally on a circle. Its rim is a ring, and it wants to come down onto a round wall, a drum, all the way around evenly. The Romans knew that. Their great dome, the Pantheon, sits on a big round wall, a fat circular tube of concrete, and it works beautifully, round dome, round base, no argument. But a round building is a limited building. It's one space, a rotunda. What if you want a huge rectangular hall, a long nave, a great open floor, corners, aisles, a building you can actually shape? Then your floor plan is a square, and now you have to land a round dome on a square hole, and there is no natural way to do it, because a circle set inside a square touches the square at only 4 points and leaves 4 gaping empty corners. So how do you carry the round rim of a heavy dome across a square room? What holds up the parts of the circle that hang out over nothing? And it gets worse because a dome doesn't just push down. This is the bit I need you to hold onto for the whole video. The way the cathedral video was about thrust, this one's about a dome trying to burst. When you load a dome, its own weight makes it want to flatten and spread. The rim pushes outward, all the way around, like an invisible ring trying to expand and split. Engineers call that outward push at the base a dome's thrust. It's hoop force, and it is relentless, and it is everywhere along the rim at once. So a dome on a square base is asking two brutal questions simultaneously. 1. How do I carry a round edge over square corners? And 2. How do I stop the whole thing shoving my supports outward and bursting the building open? Get either one wrong and you don't get a building. You get a very expensive, very beautiful pile of rubble. And the people who took that problem on didn't get it wrong. Well, I'll be straight with you, they got it half wrong the first time, and we'll get to that because it's the best part. But what they built here is, to this day, one of the gutsiest pieces of structural engineering on the planet. So let me show you how they did it. First, where we are and when, because the speed of this thing is genuinely offensive to me as a builder. We're in Constantinople, the city we now call Istanbul, the capital of the Eastern Roman world, the Byzantine Empire. And the man who ordered this building is the Emperor Justinian in the 1500s, the 500s, the 6th century, the 1500 years ago 6th century. The building is Hagia Sophia. The name means holy wisdom, and here's the number that makes my eye twitch. They built it in about 5 years. 5. It was dedicated in the year 537. A structure of this size, this daring, this far past anything anyone had attempted, up in roughly half a decade. My last big project spent longer than that, just fighting over the foundations and the permits. They put up the most structurally audacious building in the world before I could have gotten a road closure approved. But here's the detail that tells you everything about why this building is so strange and so bold. The two men Justinian handed it to were not, in the ordinary sense, architects. They weren't lifelong master builders who'd come up through the trade laying stone. They were what the Byzantines called mechanikoi. The closest word we've got is geometers, or mathematicians. Their names were Anthemius of Tralles and Isidore of Miletus, and they were men of theory. Anthemius wrote about geometry and curves and the behavior of shapes. Isidore taught and studied the mathematics of solids. These were, near enough, the theoretical physicists of their day, and they were told, take everything you know about circles and spheres and forces, and build us a dome bigger and bolder than the Romans dared. And they said yes. And that matters because you can feel it in the building. This is not a cautious tradesman's building, built the safe way because that's how it's always been done. This is a mathematician's building, a geometry problem solved at enormous scale, pushed right to the edge of what the theory could bear, by two men clever enough to attempt it, and I'd argue just slightly too clever to be scared of it. Which, as we'll see, cut both ways. So back to the impossible problem, round dome, square room, and to the single most elegant answer in this entire building. It's called a pendentive, and if you take one idea away from this video, take this one, because it's the trick that unlocked 1,000 years of architecture after it. Picture the square room. 4 huge piers, one at each corner, massive stacks of masonry driven down to the ground. Those are the real legs of the building, and everything ends up standing on those 4. Now, between the tops of those 4 piers, throw 4 gigantic arches, one along each side of the square. So now you've got a square frame in the air, 4 great arches, meeting at the 4 corners, open in the middle. Good. But the top of that arrangement is still a square outline with the tops of the arches curving up, and you still can't just plonk a round dome on it. The circle of the dome's rim is smaller than the square and floats above those four corners, with nothing under the gaps. Here's the pendentive. In each of the four corners, you build a piece of masonry shaped like a curved, sagging triangle. Imagine taking a sphere, a big smooth ball, and slicing off the bottom and the four sides, so that what's left in each corner is a downward pointing triangle of that spherical surface. Four of those, one per corner, curving inward and upward from the tops of the four piers. And the magic is in what they do at their edges. Down at the bottom, each pendentive comes to a point on top of a corner pier. It collects there. It lands on the leg. And up at the top, all four pendentives curve around and meet each other in a continuous, perfect, unbroken circle. Do you see what just happened? The pendentives are a shape-shifter made of stone. At the bottom, they are four separate points sitting on four square corners. At the top, they've merged into one smooth ring. They take a square and hand you back a circle, up in the air, ready to receive the round rim of a dome. The pendentive is the adapter. It's the piece that translates square into round, so the dome has a continuous circular ledge to sit on, and it gathers every bit of that dome's weight down into the four corner piers where you're ready for it. Square room at the floor, round dome at the sky, and a curved triangle of geometry in each corner quietly doing the translation. And think about what that buys you as a builder, because this is the real prize. Once you can put a round dome on a square, you're free. You're not trapped in a round rotunda anymore. You can build a huge rectangular hall, long, open, full of aisles and galleries and light, and still crown it with a dome. The pendentive doesn't just solve one dome. It marries the dome to every other shape of building. And that is exactly why, after Hagia Sophia, you see domes on square bases everywhere for the next 1,000 years and more, all over the world. This building is the place where that marriage was proven at full scale. Before it, the idea was a whisper. After it, it was the way you roof the world. The first time I really understood the pendentive, standing under one, I actually laughed out loud, because it's so clean. It's the kind of solution that looks obvious the instant you see it, and is borderline impossible to have thought of first. And these two geometers didn't just think of it. Plenty of the idea existed in smaller, more timid forms before them. They did it at a scale nobody had come close to, over the widest open floor anyone had roofed. They bet the whole building on the geometry holding. And then, because these were show-offs in the best possible way, they did the thing that turns a brilliant structure into a miracle. Look back up at where the dome meets those pendentives, at the ring where the round rim finally comes down onto its circular ledge. That is the single most loaded, most stressed line in the entire building. Every ounce of dome, all its weight and all its outward push, concentrates right there on that ring. That is exactly the place a careful engineer wants to be thickest, heaviest, most solid. And what did they do there? They punched it full of holes. They pierced a ring of windows, around 40 of them, straight through the base of the dome, all the way around, right along that most critical line. It's structurally cheeky to the point of madness. And it's the whole reason the dome seems to float. Because now, from down on the floor, you can't see the join. You can't see the dome landing on solid support because the support is riddled with light. The dome appears to hover over a glowing halo, disconnected from the building, held up by nothing. That's the golden chain from heaven that Procopius, Justinian's court historian, a man who was actually there, wrote about. He said the dome seemed not to rest on solid masonry, but to hang from the sky. The engineering trick and the spiritual effect are the exact same move. Hide the hardest working stone in the building behind a ring of light. Now, is that a slightly terrifying thing to do to your most stressed structural line? Yes. Yes, it is. If you brought me that drawing today, Dan, we're going to run a ring of 40 windows straight through the single most heavily loaded line in the structure, and hide the fact that it's holding anything up. I would very quietly put my coffee down and ask you to talk me through your thinking, because on paper, that's where you want the most material, not the least. They did the opposite on purpose for beauty, and they made it work mostly. Hold that thought. Hold it hard, actually, because that ring of light is about to become the center of the whole drama. Let me tell you what it's actually made of, because the materials are part of the daring. You'd think for a dome this big, you'd want the strongest, densest stone you could find. They went the other way. The dome and the great vaults are built largely of brick, lightweight brick, set in thick, thick beds of mortar, sometimes mortar layers as fat as the bricks themselves. And that's clever, because weight is the enemy up high. A lighter dome pushes out less, presses down less, and is easier to hold. They traded brute strength for lightness on purpose, up where it counts. Lower down, in the columns and the colored marble, they did something an engineer today would get in real trouble for. They went shopping across the whole empire. A lot of the fine columns and marbles in here are spolia, reused pieces, gathered from older temples and buildings around the Roman world and shipped in. Grand columns of green and purple stone, hauled from far-off sites and stood up here to hold the galleries. It's a building, assembled partly from the salvaged bones of the ancient world. And then the whole interior, every surface up high, was sheathed in gold mosaic and polished marble, so that the light coming through that ring of windows and all the others doesn't just fall, it catches and scatters, and the entire vast space glows from the inside. The structure is bold. The finish is meant to make you forget the structure entirely and just look up, slack-jawed, at a golden sky. Which, fair enough, it works. So, round dome, square room solved with pendentives, weight kept down with light brick, the whole thing up in 5 years and glowing like the inside of the sun. It's perfect. Except it wasn't, and here's the part of the story I love the most, because it's the part where the building nearly killed the idea. The first dome, the one Anthemius and Isidore built, the original, was too shallow, too flat. They built a lower, wider, gentler curve, a dome that spread out more than it rose. And I need you to understand why that's so dangerous, because it's the exact same physics as the cathedral thrust, just wearing a round hat. The flatter a dome, the harder it pushes outward at its base. A tall, steep dome sends more of its weight straight down its own sides toward the ground. A low, flat dome can't do that. Its load has nowhere to go but sideways, out, shoving on the ring, straining to burst the base. A shallow dome is a coiled spring of outward thrust, and they'd built a shallow one, and then, remember, they'd cut a ring of windows through the most loaded line of it. It held for about 20 years. And then the ground moved. Constantinople sits in a serious earthquake region, on a landscape that shudders, near a great active fault. And in the years after the building went up there were tremors and cracks, and I'd bet a lot of nervous glances upward. And then, in the year 558, a major one. The strained, flattened dome, pushing outward harder than the structure could hold, already leaning on piers that had crept outward under 20 years of relentless thrust, gave way, and part of it came down, collapsed into that golden space. The single most beautiful ceiling in the world, The one Procopius said hung from heaven on a golden chain, fell in. The chain, so to speak, let go. And I have to stop and be an honest engineer here, because this is disputed genuinely by the people who study it. How much of that failure was the shallow dome's own excessive thrust? How much was the earthquake? How much was the supports flexing and the piers leaning out under the load over those first 2 decades? The exact recipe is argued over, and you'll hear different weightings from different scholars. What is not argued is the plain fact and the plain lesson. They had built right at the edge of what they understood. They'd built the dome too flat. Its outward push was too great, and when the earth shook, the margin they didn't have ran out. The genius part and the gamble part were the same part. Now watch what they do next, because this is where you find out what these people were really made of. They don't abandon it. They don't shrink it back to a safe little dome. They fix the physics. The job went to Isidore the Younger, the nephew of Isidore of Miletus, one of the originals, so the knowledge stayed in the family, and he rebuilt the dome. And the key thing he changed is the one thing the physics was screaming for. He made it taller, steeper. He raised the curve, so instead of that low, flat, thrust-heavy shell, the new dome rises more sharply, more like the top of an egg than the bottom of a bowl. And a steeper dome, as we said, sends more of its load straight down toward the piers and shoves out sideways far less. Same trick in the end as the pointed arch in a cathedral. Gets steeper, and the outward push drops. He rebuilt the dome higher and meaner and better behaved. And that, the second dome, the corrected one, is essentially the dome you're standing under today. So the ceiling over your head is not the first draft. It's the fix. It's version 2, built by a man who had the rubble of version 1 to learn from, and who understood because the building had just taught everyone the hard way exactly which direction the answer lay. They reached too far, the reach fell, and then they reached again smarter. And here's the thing nobody tells you, the thing that changed how I see this building completely. That wasn't the end of it. Holding this dome up has been a fight that never actually stopped, a 1,500-year running battle between this ceiling and gravity, with humans frantically refereeing the whole time. Because the corrected dome, for all that it was better, still pushes out. Every dome does forever, as long as it stands. And the great piers underneath have slowly, over centuries, been shoved outward and made to lean by that relentless push. So the building has been braced and propped and reinforced again and again down the years. Buttresses, big external masses of masonry, were piled against the outside to push back in against the dome's outward shove and hold the piers in line. There were more partial collapses across the centuries. Sections of dome and arch that came down in later earthquakes and had to be rebuilt through the Byzantine centuries. And then, after the building's later life began, through the Ottoman centuries as well, when great architects of that era came in and added their own reinforcements to keep the thing standing. So this dome you're looking at isn't a single frozen act of genius from the year 537. It's more like a patient, a magnificent, fragile, world-treasured patient, that a long relay of engineers across 15 centuries have kept alive with brace after brace after brace. Every generation that inherited it also inherited the job of not letting it fall. And they didn't. That, to me, is almost more impressive than the building. The original swing was audacious. The 1,500-year save is heroic, and I want to be honest about the numbers too, the way I'd want someone to be honest with me. You'll see the dome's width quoted as 31 meters, 32, 33, 102 feet, 108, depending on which source you read and exactly where they measured. Because a dome that's been rebuilt and braced and nudged over 15 centuries isn't a perfect circle anymore. It's slightly egg-shaped, it's shifted. The number depends on the axis. So I'm giving you a range on purpose, not a false decimal, and that's not me being vague, that's me being accurate. Anyone who tells you the exact diameter to the centimeter is rounding off the reality of a living, moving, endlessly repaired structure. The honest answer is roughly 100 feet across, and it has never once stopped needing us. And I should tell you, plainly and respectfully, what happened to this place over that long life, because it's had several. For the better part of 1,000 years, it was the great cathedral of Byzantine Constantinople, the beating heart of the Eastern Christian world. Then, after the Ottoman conquest of the city in 1453, it became a mosque, and the 4 slender minarets you see on the corners outside were added in that era. In the 20th century, it was turned into a museum, open to all as a monument. And in 2020, it became a working mosque once more. 4 lives in one building under one dome. I'm an engineer, not a politician, and I'll leave the meaning of all that to the people it belongs to. What I'll say is this. Through every one of those chapters, the thing everyone agreed on, across empires and centuries and faiths, was that this dome must not be allowed to fall. And so it hasn't. And that's where I want to turn this around on you, because I didn't bring you in under this dome just to admire the ceiling. Here's what I keep coming back to, as a man whose entire job is to be certain before he builds. These 2 geometers took on a problem they did not fully have the tools to solve. They did not have my equations. They could not calculate in advance to 3 decimal places whether that dome would hold. They reasoned it out with geometry and proportion and nerve. They pushed it right to the edge of what they understood and passed it the first time. They got it wrong. It fell. And then they learned exactly where the edge was, and they built it again on the right side of that line. And it has stood for 1,500 years through dozens of earthquakes that have flattened lesser buildings all around it. The whole thing, the genius and the collapse and the fix and the endless bracing, is really one story. And it's not a story about domes. It's about how you make anything that's never been made before, when nobody can hand you the numbers in advance. You learn everything the people before you learned. You reason it out as far as reason will take you. And then, at some point, you have to commit to something bigger than anyone has proven will stand and strike the scaffolding and find out. And sometimes it holds and it's a miracle, and sometimes it comes down. And if you're the kind of person who rebuilds, that rubble is the most valuable thing you own, because now you know precisely where the edge is, which is knowledge nobody who played it safe will ever have. Anthemius and Isidore didn't build a perfect dome. They built a daring one, watched it fall, and built a wiser one. And the wiser one is still up there, 15 centuries later, floating on its ring of light. I think the reaching and the falling and the rebuilding are not 3 separate parts of that story. I think they are the whole method. I think that's just what it looks like to build something real at the edge of what you know. I think about my own worst job when I stand under here, the one my crew still calls the over-budget nightmare, the project that ran so far past its numbers it became a legend on site. And you know what I got wrong on it. I reached, which was right, but I left myself no margin, no room to be wrong, no second dome. First thing that went sideways went all the way. These 2 geometers, with a fraction of what I had, reached further than I did, and when it fell, they had the humility and the nerve to build it again better. Reach and leave yourself a way to survive being wrong and be willing to rebuild. That's the dome. That's the whole trick. So that's my question for you, and I do read the comments. I read all of them. Here it is. When have you built something you couldn't calculate in advance, reached for something past anything you'd proven you could do, and had to just commit and find out whether it would hold? Did it hold? Or did it come down on you, and if it did you rebuild it steeper and smarter, the way they rebuilt this dome, or did you walk away? I genuinely want to know. I'd bet every single person watching has one dome that held and one that fell. Tell me about both, down in the comments. I'm going to go back to my site and try, one more time, to explain to my foreman Mike why the Byzantines solved round dome on a square room with a curved triangle of geometry in each corner and not, as Mike would have it, by just making the room round and moving on with our lives. My intern Priya already asked me the good question. She looked at that ring of windows through the most stressed line in the building and said, "Isn't that exactly where you'd want it solid?" Then yeah, Priya, that's the point. That's the nerve of the whole thing. Try getting that past a modern safety inspector. If you like standing under something impossible and actually working out how it holds, no magic, no mystery, just geometry and brick and the nerve of two mathematicians who reached too far, fell, and reached again, then subscribe and come back, because next time I've got another one that's still standing and still showing us up. My name's Dan. Mind the load. And the next time someone tells you they don't build them like they used to stand under this dome, find that ring of light and tell them the truth. They built the boldest ceiling in the world, they watched it fall, and they built it again so well that it's still floating 1,500 years later, and we are still, quietly, trying to work out exactly how.